Hello everyone, welcome to today's lecture on probability and statistics. Today we are diving into an exciting topic, conditional probability. This is a key concept that helps us understand how the likelihood of one event changes when we know something else has happened. We will see the definition and basics of conditional probability, the multiplication rule, Bayes theorem, independence, and we will try many examples and practical questions. Let's get started. Conditional probability is the probability of one event happening given that another event has already occurred. Think of it like this. If it's raining outside, what's the chance you'll grab an umbrella? That given that we have here conditional probability of A given that B has already occurred. That given part changes the odds. Now let's put a mathematical face to the conditional probability. For two events like event A and event B, with the condition that the probability of B is greater than 0, not 0, it means already occurred. The conditional probability of A given B, we write like this, A given B. Probability of A cap B, right, or intersection of A and B is the probability of both A and B happening. Probability of both A and B happening divided by the probability of B. So probability of A intersection B or A cap B divided by probability of B. This makes sense, right? We are narrowing down our focus to just the case where B occurs. Let's see this in action with example next. Imagine a factory with two assembly lines, A and A prime. So these two are assembly lines and they make some complex components. Line A is older than A prime and it produces 8 components, so 2 will be defective. 2 will be defective. It means event B. And 6 are not defective B prime. It means they are okay. Line A prime with newer equipment can make one defective and none okay. We can see this table here that's summarizing this one. So line A, 2 defective, 6 okay. Line A prime has a better performance, 1 defective and non-satisfactory. A sales manager picks up one of these 18. So we have generated total 80, right? So we have totally 18 products. The sales manager picks up one component randomly for demonstration. Then the probability they pick a line component A, the probability of line A component has been selected. We show by probability of A is equal to NA, right? NA divided by N. So what is NA? 8. What is N? 18. So 8 divided by 18, we get 44.44, which is equal to 44%, right? So the probability that the sales manager randomly takes one component from A line is 44%. So continuing our example, if the chosen component is defective, we show by event B, there are only 3 defective components, 2 from line A and 1 from line A prime. Now, what's the probability that this selected defective comes from line A? Right? So we show by probability of A given B. Out of those 3 defectives, 2 are from line A. So probability of A given B is 2 out of 3, Or you can say 2 out of 18, 3 out of 18. These 2 out of 18 is too defective from line A here, and 3 is the total defective, right? So we show PA cap B divided probability of B, it is equal to 66%. So we easily can understand that how the formula match the intuition that we had. Here is another example. Suppose 60% of people buying a digital camera, 60% of them get an optional memory card. So we show this one by event A, memory card purchased along with the digital camera. What percentage? 60%. Then we have event B, where 40% of customers also they get an extra battery, right? We show by event B. So, and that is 30% get both of them, right? Get both of them. And it means both event A and event B. If we pick up a buyer randomly, what is the probability they got a memory card given they bought a battery? It says probability of A given B. So the probability of event A is 60%. Probability of event B is 40%. Probability of both of them intersection is 30%. Then the probability that an optional card was also purchased is equal to probability of A cap B divided by probability of B. 30 by 40 is 75%. What about the reverse? If we say probability of B given A, probability of battery given memory card is probability of A cap B by probability of A, which is 30 by 60 is 50%. This shows how conditional probabilities can differ depending on what is given. Let's talk about the multiplication rule. It is a handy way to find the probability of two events happening together. Probability of A intersection B, or AND. It means both of them happen together, right? You can say AND operator, right? So probability of A and B is probability of A given B multiply probability of B, right? So it's simple but powerful. For example, if we have three events, A1, A2, and A3, we can extend this. The probability of all three happening is equal to probability of A1, probability of A2, probability of A3, and all are and, right? Is equal to probability of A3 given both A1 and A2 multiply probability of A1 and A2 is equal to probability of A3 given both A1, A2 multiply probability of A2, A1, A1, right? One parenthesis is missed here. So the probability of all three happening is based on this one. Then we can break that down further to probability of 2 given A1 times probability of A1 that you can see here. It's like a chain of dependencies. We will see more applications of this later. Next up is the law of total probability, a stepping stone to Bayes theorem. Imagine events like A1, A2, A3 to AK that cover all possibilities. They are mutually exclusive and exhaustive. What is the meaning of mutually exclusive? This means that no two of the events can happen at the same time, right? They are exclusive. They have no common parts, like what you had already. And exhaustive means that the events together cover all probabilities, right? So it means A plus B is universal, right? Is equal to universal. So for any event B, its probability is the sum of probability B given A times probability of A for all A to K, right? It means probability of B given A2 multiply probability of A2 to probability of B given AK multiply probability of AK. Think of this as breaking B into pieces based on these conditions. The formula is this nice sum here that we can see. It will be sum of I from 1 to k, probability of BAI. It means I can be 1, 2, 3 up to k, and here the same 1, 2, 3. This is how the law of probability works. Here is an email example. Someone has three accounts, three different email accounts he has. He gets 70% of messages come to email account 1, 20% go to account 2, and the remaining go to account 3. Spam rate differs. 1% goes to account 1, 2% for account 2, right? 2% for account 2 and 5% for account 3. It means this guy has three accounts, account 1, 2, 3. The first account always he get almost 70% of emails, 20% goes to account 2 and 10% go to account 3. Out of the emails that he receives, 1% in account 1 is spam, 2% in account 2, and 5% in account 3 spam, unwanted emails. Now, what is the probability a random message is spam? We call it as event B. So we show AI event 1, 2, 3 messages is from account 1. A1 is, so A1 is, it means message is from account 1. A2 message is from account 2, and A3 message is from account 3. Then the event B is the message is spam, right? So now probability of A1 is 70%, probability of A2 is 20%, and probability of A3 is 10%. Probability of B given A1, it means the message spam is from account 1 is 1%. Probability that the spam message is from email 2 is 2% and 5% for the last one. Now, what is the probability that a random message is a spam? So, based on the law of total probability, PB is equal to PB given A multiply PA1. PB given A1 multiply A1. PB given A2 multiply P2. PB given A3 multiply this one. So this one multiply this one plus this one multiply this one plus this one multiply this one plus all become here what 1.6%. Not too spammy, thankfully. Now we come to Bayes theorem. It flips conditional probability around. If A1, A2 to AK are mutually exclusive and exhaustive, as we defined already, and we know that probability of B, then we can find out probability of AJ given B. This is called as the posterior probability. What is the posterior probability? This is updated probability of an event occurring after taking into account new evidence or information. And it's calculated based on Bayes theorem, right? Then we say probability of AJ given B is equal to probability of AJ cap B divided by probability of B, which is equal to probability of B given AJ multiply probability of AJ divided by sum of probabilities from 1 to k, probability of B given AI multiply probability of A. So this probability of AJ, these values are prior probability. These are called as prior probabilities. This is called as posterior probability, right? And this PB that we have here often come from the law of total probability. It's like detective work. Given the evidence B, what is the chance of a specific cause AJ? So this AJ is a reason. This is a cause, right? And this probability of B is an evidence, right? All together we call it as posterior probability. We will explore this more later. Let's talk about independence. Two events A and B are called as independence if one happening does not affect the other. Like, for example, you flip a coin twice. What comes from the first try does not have any impact to the next one. And what comes in the second trial does not get any impact from the previous one. So mathematically, we say probability of A given B is equal to probability of A. If that's true, then probability of B given A also is equal to the probability of B. This is a big deal because it simplifies things a lot, as we will see next. For independent events, the multiplication rule gets even simpler. If A and B are independent, right, then A cap B is just equal to probability of A give multiply probability of B. No conditional stuff here. This proposition is key. It's both a definition and a test for independence. So we say if A and B are independent, then probability of A and B is equal to probability of A multiply probability of B. Let's try it out with some example. Here is a real world case. A company's washing machine have 30% of needing warranty service, and we call it as event A. The washer needs service while under warranty. And their dryers have 10%, so probability of B. Event B, the dryer needs service while. So the probability of event A is 30%, while the probability of event B is 10%. Now, if someone buys both and assuming independence, it means one machine's failure does not affect the other one. What is the chance both need service? We call it as probability of A cap B, which is probability of A multiply probability of B. 30% multiply 10% is 3%. This is the same as 3%. Independence makes this calculation a breeze. What about more than two events? Events like A1, A2 up to AN are mutually independent if the probability of any subset of them happening together is the product of their individual probability, right? Product of them all together. That's true for any group of 2, 3, or more events up to n. So we can see here, this formula shows for the indices like AI1, I2 up to IK. So probability of AI1 and up to AIK is probability of AI1 multiply probability of AI2 up to probability of AIK. It's a strong condition and we will see it in a system example next. Imagine a system with 6 cells, 1, 2, 3, 4, 5, 6, right? 1, 2, 3 are in one line and another 5, 4, 6 are in the another line. Each cell has a probability of 90% of lasting past time t0, and they are also independent. The system works if at least one subsystem works. It means all three work okay, right? It means if any of this cell has a problem, this line is out of order. But if three work okay, it's okay. And if one line is out of order, still the second line can works, right? So each cell has a 90% chance of lasting past time t0, and if one line is okay, it means the system survives. The probability is PA1 cap PA2 cap PA3 plus this is OR, right? These are and, right? So I can say and, or, and, right? So it means all these three should work, but any of these cascade work, it's okay. That 90% cube. So we can say zero point 0.9 multiply 0 0.9 multiply 0 0.9 plus 0 0.9 multiply 0 0.9 multiply 0 0.9 and minus, then we will remove the overlap. So this is the overlap. So what happens here? The probability of A1 cap, probability of A2 cap, probability of A3 plus probability of A4 cap, probability of A5 cap, probability of A6 minus the overlap, right? So which give us 927. So that's 0.9 cube, which is, so from here we will get like 0.729 minus 0.9 here, minus 0.9 to the 6, minus 0.9 to the 6, which is, this one is something like 0.531, and the result will be 927, which is equal to 92.7%. Independence lets us multiply like this. An alternative way to the previous example, same example but from a different angle. The system failed only if both system fails, right? So the probability that system fails, right? It means we can say the probability that system life, so probability that system life is greater than t0 is 1 minus probability, 1 minus probability both fail, right? 1 minus p subsystem life is greater than t0 square, right? It can be say 1 minus 1 minus 0.9 cube square. Then finally we can come to here, right? So two methods will give us the same answer, but from different angle. Consistency is beautiful. Now tweak the system. Connect ties across columns. So it fails if any column, like pairs of cells, fails. So you can see here we added these lines here, right? System life exceeds T0 only if all three columns survive, right? So it means one of these one should be there, one of them one should be there, one of this one should be there, right? So these two together, these two together, these two together, right? A column fails if both cell fails. That is 1 minus 0.9, right? 1 minus 0.9 squared, or you can say 0.1. A column survives with the probability of 99%. So all three surviving is 0.99, right? 0.99 cube, okay? And it is about 97%. So a column survives with the probability of 0.99. So all three surviving is 99.9%. 0.99 cube is about 97%. Changing the setup, change the odds. Now we're gonna try some practical examples. A student has a bag of 20 candies, so total 20 candies, and out of them 12 are chocolates, so 12C, and 8 are fruit flavored, right? Out of these chocolates, 3 are dark, right? And we show by D. And out of these fruit flavored, 2 are sour, right? 2 of them are sour. If a candy is randomly picked up and known to be a chocolate, what is the probability that it is a dark chocolate? So once again, a student has 20 candies. 12 are chocolate and 8 are fruit flavored. Out of chocolates, 3 are dark, and out of these 8 fruit flavored, 2 are sour, right? So if a candy is randomly picked and known to be chocolate, what is the probability that it is a dark chocolate? So we need to find out probability of D given C. The probability of dark chocolate given it's a chocolate. So probability of D given C is equal to probability of D and C divided by probability of C. PC, PC is the number of chocolates divided by total candies. So I can say that PC is equal to 12 divided by 20, which is 0.6 chocolates out of total candies. PDC, I will write it here. PD and C is the event of picking a dark chocolate, which is already a subset of chocolate. So PD and C is number of dark chocolates divided by total candies. So I can say 3 divided by 20, which is 0.15 dark chocolates out of total candies. So PD given C is equal to PD and C divided by PC, which is equal to 0.15 divided by 0.6 is equal to 25. Alternatively, since it's a given chocolate, it's 3 out of 12. You can say also 3 out of 12 is equal to 25. So answer is 25%. Next, at the cafe, 40% of customers order for coffee, right? And 30% ask for pastries, shown by P. If ordering coffee and pastries are independent events, what is the probability a customer order both? So we say for independence event, we say PC and P is equal to PC multiply PP, right? So PC is what? 40%, we can show by like this. Probability of a coffee and probability of pastries is 0.3, right? So probability of P, C, and P is equal to 40% multiply 30% is equal to 12%, right? This is the probability a customer orders both coffee and pastries. Next, a student uses 3 applications, right? So application A, application B, and application C. So he uses 50% application A, 50% of study time, and this one 30%, and this one 20%. Total 100%. The probability of finishing homework on time is 80% from application A, 70%, and this one 90%. So the probability of finishing homework on time is 80% with application A, 70% with application B, and 90% with application C. Application C is better compared to A and B. What is the probability that a student finish homework on time, right? So we use the law of total probability. We say probability of PH is equal to probability of H given A multiply probability of A. This plus probability of H, it means finishing homework on time, given B multiply probability of B, plus P PH given C multiply probability of C, right? So probability of A is what? 50%. So in here, so this one is all together. This one equals. So for this one, for the PH given A and PA, it will be probability of A is 50%, right? 0.5, right? Then I can say 0.5. This one is 80.8. So I can say 0.5 multiply 0.8, which is equal to 0.4, right? Then probability of B is 30%. Probability of H given B is 70%. So I can say 30% multiply 70% is equal to 21%. Then probability of C is 20%, right? Probability of H given C is 90%. Then I can say 90% multiply 20%, which is equal to 18%. Then sum up all together, we sum up this all together, then we will get 79%. It means the probability that the student finish homework on time is 79%. Next, a factory has two machines. Machine X makes 60% of products and machine Y makes 40% of products. Machine X has a defect rate of 5%, while machine Y has a defect percent of 2%. It means 5% of the products made by X has a problem, while 2% of products made by machine Y has a problem, right? So if a defective product is found, what is the probability that it came from machine X? So we want to find out Px given D. It means we know that this product that we have selected is defective. We want to find out what is the probability that it came from line X or machine X. Based on Bayes theorem, we say that this is probability of X given D is equal to probability of D given X multiply probability of X divided by probability of D. Probability of X is 60%, right? Probability of D given X is 5%. Probability of Y is equal to 4%, and probability of D given y is equal to 2%, right? So we want to find out the probability of defect. Probability of defect is equal to probability of d given x multiply probability of x plus probability of d given y multiply probability of y, right? So here it will be 0.5 multiply 0.6 plus 0.02 multiply 0.4, right? This one will be 0.03, 0.008, which give us 0.038, right? So probability of xd is equal to probability of dx, d given x multiply probability of x divided by probability of d. So this will be 0.05 multiply 0.6 divided by 0.38, which is equal to, after calculation, we will get like 7895. So I can say if a defective product is found, the probability that it came from machine X is 79%. A system has two parallel components, each with three parts in series. Each part has a 95% chance of working and all parts are independent. What is the probability that system works? It means at least one component functions. The system works if at least one component works. It means the probability of part works is equal to 95%. The probability that component works is equal to 95% multiply 95% multiply 95%, right? And all together will be equal to 85 7 something, right? It means all three parts works. Then the probability that components fail is equal to 1 minus 0.857, right? Which is equal to 142 something. Then the probability that both components failed is equal to 142 multiply 142, which is equal to approximately 0.0203. Then the probability that system works correctly is equal to 1 minus probability of both fails, which is equal to 1 minus 0.0203, which is approximately 0.9796. So by the probability of almost 98%, the system works fine. It means at least one component functions correctly. That's it for today. Conditional probability defines how events influence each other. The multiplication rule helps compute joint probabilities. Bayes theorem updates probabilities with new evidence. And independent identifies when events do not affect each other. We have tried all those important topics with several examples and practical questions. If you have questions, please feel free to write a comment below this video. Conditional probability is everywhere. think about how you use if in daily decisions. Please practice these examples and you will master it. Thank you for your attention and see you next time.